I'll begin then. Hi, everyone. My name is Jaeyun Sung, and I'm a computational biologist and assistant professor at the Mayo Clinic in Minnesota, in the USA. For my short talk today, I'll be presenting on our recently published paper in Nature Communications titled Gut Microbiome Wellness Index 2 Enhances Health Status Prediction from Gut Taxonomic Profiles. Okay, so I have an important question for the audience. How do we measure gut dysbiosis? Wouldn't you want to know whether your gut microbiome is in good shape or not? Well, we know that there are thousands to 10,000s of so called gut microbiome disease correlations and associations in the literature, but you need to ask, are these useful? Today, we don't have a widely acknowledged standardized tool that can take a gut microbiome sample and judge, oh, you're in great shape. Your gut microbiome looks like that of someone who has a disease. Sort of like an alarm bell that goes off in your car when there's something wrong with the engine or brakes or transmission. If we're really interested in making a translational impact in gut microbiome science, I'd argue that we need a quantitative index that finds generalizable signatures of the healthy gut microbiome and can provide a grade like an A for excellent, to C where you pass, and F or for a failing grade. Um, so we tried to solve the problem in our paper published in August. We provide the Gut Microbiome Wellness Index 2 or GMWI 2. It has a 2 on it since it's the second iteration of our prototype published in 2020. GMWI 2 is a machine learning based tool that assesses health from a gut microbiome profile. And you can't, well, I'd argue that you can't study anything if you can't define what it is you're trying to study. So in our case, healthy was defined as not having a disease or disease free. And non healthy was defined as harboring a disease independent of what that disease may be. This, of course, isn't the perfect definition, but again, to study something, you need to first define it. And we thought that this was the most practical way to study what the healthy gut microbiome is. If anyone has a better definition that works at scale, please let me know. Anyway, to move on, our machine learning algorithm tells you the likelihood of being either healthy or non healthy. It was trained on 8,069 stool shotgun metagenomes from 54 published studies, and the performance was validated on 1,140 metagenome samples from 6 additional published studies. So, this entire study was done by pulling together public datasets. This is part of our study design figure where we described how we pulled over 8,000 stool shotgun metagenomes together. I don't have the time to go through all the details of our study subject and sample exclusion criteria, but I do want to mention that we ended up having 5,547 samples of healthy, so not having a disease, and over 2,500 samples of non-healthy from people with 11 different conditions, including cardiovascular disease, colorectal cancer, 2 different inflammatory bowel diseases, liver cirrhosis, rheumatoid arthritis, and type 2 diabetes. Our samples were also from all over the world, 26 countries from 6 continents, and about an equal representation of both males and females. Here's a PCA plot of what pooling 8,069 samples looks like. Each point represents a sample or person. Blue being healthy and red being non-healthy. You can see that despite the wide overlap, there seems to be a separation between the 2 study groups. So how do we create a classifier out of this? I mentioned that the Gut Microbiome Wellness Index, or GMWI2, is a machine learning tool. Specifically, we used a lasso or the L1 norm penalized logistic regression model. Now all the mathematical details of our model are in the paper, but I'll briefly summarize. As shown in this equation here, the transpose of the vector of coefficients, which we obtained using this objective function here, is used to form a product with a gut microbiome taxonomic profile, and that gives us a score for a particular gut microbiome sample X test. So if you get a score for your gut microbiome, and how classification works is that if it's below a certain magnitude cutoff, like 0, then you're non-healthy. If you're exactly 0, then you don't make a decision or defer. And if you're above 0, then you're healthy. So in the simplest sense, a positive GMWI2 means you're healthy, and a negative GMWI2 means you're non-healthy. So how do we do? We find that GMWI2 does a lot better than its predecessor, GMWI1 and alpha diversity indices in separating healthy from non-healthy groups, as you can tell by the Cliffs delta effect size, or D, where the closer you are to +1 or -1, you're reaching perfect separation. GMWI2 has the highest Cliffs delta, as you can see by the Ds here. Um, and it does much better in classifying healthy versus non-healthy than GMWI1. And this is important since alpha diversity indices, which are traditionally used in the literature to denote health, although they weren't really designed for such purposes, have no intrinsic cutoff to distinguish different classes. Here's GMWI2 scores for all the 12 separate health and disease conditions, with the healthy group at the very left, um, having the highest distribution of scores, while interestingly, colon cancer, liver cirrhosis, and cardiovascular disease had the lowest scores. The gut microbiome did the worst. One important thing I'd like to mention is that we can use different GMW2 cutoffs for classification, and that gives us the liberty to choose not to make a class prediction when a score is below a certain cutoff, or in other words, defer to not make a prediction when the algorithm is not confident. This is actually what happens in self-driving cars when the cars defer the steering wheel to the driver in case of a hurricane or blizzard when the cameras cannot see ahead. So to illustrate why this may be advantageous, is that if you look at the ends of the distributions in blue and red, you see that towards the more positive and more negative ends, you see much more of one group versus the other. So rather than setting the cutoff to 0, you can have higher cutoffs like 0.5 or 1. And we show the outcome of that here. We find that as we increase the cutoffs, starting from 0 to zero point 0.5 and 1, and 0.5 and 1 are just examples. They don't have to be this particular number. We increase the accuracy of phenotype classification from 79.9%, which I show here, to 85.8 to 91.0. Although we do sacrifice the number of samples we can retain for classification. But still, at a stringent cutoff, we can take a stool sample from 10 people and correctly predict whether someone has a disease or not for 9 of those people. This sums up how we did in the training data. And we also show in the paper that our accuracies are pretty much robust in cross-validation. As most of us know, holding up, or at least not totally bombing, on independent cohorts is the gold standard for any biomarker. So here we show how GMWI2 does on an external cohort consisting of 1,140 stool metagenome samples from 6 published studies. The distribution of healthy and non-healthy are as such, with an accuracy of classification of 72.1, and this grows to 75.4 to 80.1 as we increase the thresholds the way I mentioned earlier. The healthy groups delineated by the study are generally positive, and the non-healthy groups spanning ankylosing spondylitis, and this is an autoimmune disease of the spine, Parkinson's disease, which was really interesting given that our training data didn't consist of any patients with neurodegenerative disorders, and pancreatic cancer were generally negative. These results show that GMWI2 translates, I would say, reasonably well to validation data. In the last part of the paper, we applied GMWI2 on existing longitudinal cohorts to show the proof of concept of gut health tracking using our index, and we demonstrate this across 4 different themes or scenarios. Among these 4 scenarios, I'll talk about how the Gut Microbiome Wellness Index changes when you get rid of fiber in your diet. So very briefly, we find that for those on omnivore diets or vegan diets, the wellness index stays relatively stable over the course of 5 to 6 days. But for the exclusive enteral nutrition or EEN diet, which the participants were eating a totally fiber-free synthetic powder diet from a specific food company, GMW2 began to drop almost immediately after starting this powder diet, starting from day 2. So again, a lesson to not skip fiber in your diet. To conclude, we developed an open source computational tool to monitor gut health. I must clarify that, and this gets misunderstood a lot, understood a lot, but I'd like to clarify that this index is not for diagnosing a disease. I can argue that this is not a good idea, and I can clarify that in the Q&A. And also in the clinic, we already have good enough tests and biomarkers for disease diagnosis, but this index was built for people. So our index was built for people who are already in good shape but still want to maximize their wellness. So I'm talking about the David Goggins of the world, the Peter Attias of the world, and some of you may know Brian Johnsons of the world. Persons at risk for health problems, such as those entering mid-age, well into mid-age, or going into old age, or already in old age, or those recovering from a disease who want to check on their gut. And this is all possible from a stool sample. If you have any questions, I'm available by email, LinkedIn, or X. I hope you'll find our tool useful for your research projects, whether that may be in personalized nutrition, gut recovery, or anything else. Thank you so much for listening.